Hello everyone, our paper for today identifying the rating of unified power controller according to unbalanced distribution system requirements. Authors are Ahmed Mohammed Al-Khouli, Professor Dmitry Ivanovich Panfilov, and Dr. Ahmed Said Al-Gibel. In this presentation, I would like to introduce you to some important concerns involving the technical indicators of electrical distribution system. The main goal of these systems is to transmit and distribute the electrical energy to customers in efficient, affordable, and reliable manner. However, there are several technical indicators that must be considered in order to achieve this goal. Includes phase balance, voltage regulation, rapid voltage rise, electrical losses, system security, and system and supply reliability. One of the most common causes of the voltage imbalance in electrical power system is unbalancing loading. This occurs when the three-phase electrical system has a different amount of current flowing in each phase. This can lead to problems such as voltage fluctuation and negative sequence current, which can damage or reduce the efficiency of the electrical equipment. To prevent that, it's important to avoid unbalanced loading as much as possible. Additionally, the voltage imbalance at the point where the different systems are connected should not exceed 3% according to GOST standard. One of the solutions to solve this problem is UPC or Unified Power Controller. Unified Power Controller is a device that generates a balanced current based on the load mode of the operation. The symmetrical component method is used to develop requirements and determine the UPC rating. Additionally, power flow analysis employing the Newton-Raphson methods is conducted to deduce the device rating in our study. The main contribution of this paper is determine the UPC rating. To do so, we evaluate an unbalancing distribution system under different loading conditions to assess the maximum need of power balancing provided by UPC. The effect of UPC may be only the balancing of active and reactive power between the phases, or balancing an active reactive power and compensating the total reactive power required by the load connected at the same bus. Uh, in summary, this paper main contribution is evaluating the rating of UPC in both mode of operation, the first mode and second mode. Our agenda, including principle of operation of designed UPC and design methodology, the rating design methodology of UPC, then the case study used to prove this methodology, then the results and implementation, and symmetrical components that show the current sharing from the device to the grid. Finally, the conclusion. Principle of operation of UPC. The figure illustrates a basic circuit of UPC, which include two units, BCU or power control unit and RPCU or reactive power controlling unit. It is managed by control system. The control system measures the voltage and the current in the load phases to calculate their power and set a control action to generate a controllable parameter for uniform redistribution of active powers in the three phases. An independent analysis and calculation of controllable parameters are done separately for each phases. That's manage us to make the UPC operate in two modes, which mentioned before. Section we introduce the power balancing mode for in UPC. The first mode, when the UPC compensate only the negative and zero current components. This lead to balance active and reactive load, and this mathematically shown here in this equation. The second mode, when the reactive power control unit is activated through the compensation of reactive part of the positive current component. This can be presented mathematically in this equation. The rating of the balancing device determined by the apparent power, which is calculated from the maximum required current and maximum applied voltage of the device. Additionally, the rating of the reactive power part of UPC is defined by the maximum load reactive power. The first step in this design methodology is getting the data 24-hour data from the real system database. This load data are fed into a static model of a system. This model contains information about this distribution system. Then an ABC current is calculated. The ABC current is identified by Newton-Raphson, and then the negative component is sorted to select the maximum negative component or value over the day, and we then at this loading condition we cancel the positive negative component and construct the ABC current for the this hour without the positive component, and calculate the voltage target at the base at this hour. Then the UPC rating is attempted. Our case study is IEEE 13 bus system. This IEEE consisted of 13 nodes. The system has a rated voltage of 4.16 kilovolt. Supplied total active power is 3.4 megawatt and total reactive power 4.0.3 megawatt. Proposed devices is chosen to install in two buses according to load flow study. Our load flow study uses the Newton-Raphson method for unbalancing distribution system to get the results. The two locations are 634 and 675. The ratio or the imbalance ratio is a ratio between the negative voltage component and the positive voltage component. We done this study over 24 hours in the IEEE 13 bus, so we adopt a standard bus from another standard system called European urban system. The load profile over 24 hours is shown here in this figure, and the load distribution over the bus is shown here for the IEEE 13 bus is shown here. We can show that at hour 12 is the most hit bus 634. The ABC is calculated using load flow study. Shown here, we can observe that phase A is heavily loaded in comparison to phase B and C, and this is a positive and zero sequence component. So we can show that the negative and zero component is very high because the phase A is loaded compared to phase B and C, and the same is done to bus 675. This is phase A, B, and C, and we can see that phase A is heavily loaded compared to phase B and C, and also the negative and zero component is very high compared to positive component. The maximum negative component for buses mentioned before 634 and 655 occurs at the hour 12 and 11 respectively. This hour the design process is executed. The current are determined in ABC and then transformed in a symmetrical component, positive and negative and zero. Then the positive current is cancelled to get the device current. To get the operational voltage for this device, the load flow study is performed under the condition of balanced loads at the targeted bus. This table shows the final current and the final voltage for each bus and for each phase for each device. The resulting rating for both active control unit is 0.5 megawatt or zero point 0.6 for bus number 634, while the active control unit for bus 675 is 1.6 megawatt. While the reactive control unit is designed to be equal to installed load reactive power or higher at the installed bus, so for bus 634 is equal to 0.4 megavar, and for bus 675 is equal to 0.6 megavar. This phasors diagram shows the contribution of the device to the grid. The green is showing the contribution of device in phase B and A and C, and the blue is the load current, and uh, the orange is the load current after the balanced operation. And this symmetrical component at the bus 634, the same is for the bus 675. The device current is in green and the load current is in blue, uh, and the balanced current after the balancing operation is in orange. And this is a symmetrical component. In conclusion, a design methodology for UPC device for power balancing and reactive power compensation has been developed. This methodology mainly depends on the identification of unbalanced distribution system requirements, which have been identified using Newton-Raphson method. The development methodology is used to determine the rating of both active and reactive control unit. The UPC device may be designed for only one purpose or multiple purposes, such as power balancing, reactive power compensation, or both. The UPC rating identification has been applied to a standard IEEE 13 bus system loaded with a standard load profile. The developed methodology is represented as a general technique that can be applied to any unbalanced distribution system if essential system data such as voltage level, system configuration, and load profile are available. Thank you. Any question?